Hello, can you hear me okay? It's magic technology, how we can fix it, how we want it to work. Okay. Hello, my name is Emily Stolfo, and I'm going to give a talk called Beauty and the Beast, Your Code and Distributed Systems. I'm a Ruby engineer at Elastic, where I've been working for a little over a year on the client to Elasticsearch. Before that, I worked at MongoDB for 6 years on the driver to the database, to MongoDB. I'm an adjunct faculty at Columbia University, a resident of Berlin. Oops, going ahead too quickly. Resident of Berlin, I'm originally from New York, and I'm a maintainer of these gems. And I just gave away my punchline because you saw the slide. But anyway, I said I have worked on the client's team at Elastic because this is no longer valid, this list, because now I'm working on this gem. I've moved to the APM team at Elastic. I'll be working on the Ruby agent to the APM product. And let's make the font a little bigger so it looks more impressive. So this is my friend Bear. He lives in Berlin, and he's an application developer. And like a lot of application developers, he's spent many years writing code that works with a distributed system, but he's never had the chance to sit down and really study what distributed systems are and how they work. So he's been able to go many years thinking that distributed systems are simple. But distributed systems are actually quite complex. And what do I mean by he thinks that they're simple? Let's look at some code that he would write. So in this code, he uses a DB object that he gets from the client, and he pings the database. He gets a positive response back, so then he knows he can send a write, and it'll be successful. What could go wrong? But this code can also show you, or show Bear, how distributed systems can be complex, because anything can happen between the ping and the write. A node could go down, there could be a network outage, there could be an election, so the write that's going to a node that can handle a write no longer can handle that write because it's no longer a primary or a master, or whatever it's called in the distributed system. So what Bear has to understand is that distributed systems are complex, but they're designed so that your code can be simple. So he's been able to go so many years thinking they're simple because they mean it for you to think that they're simple. And even more, what's important for him to understand is that his application shares some characteristics with distributed systems. We don't write applications today that are just one single application and one central database. We write applications that have 1,000 different servers and APIs and endpoints and background processes. So an application today resembles a distributed system in a way. It shares some characteristics with a distributed system. So with a deeper knowledge of how distributed systems work, Bear can understand how its application works and write better code. So this talk will be about the education of Bear. We'll talk about the beast. We'll define a distributed system. We'll talk about some concepts associated with distributed systems. And then we'll look at the beauty, his code. We'll look at how he can handle errors and retries and use the gem APIs more effectively and testing. Okay, so let's start with what is a distributed system? Textbook definition. Autonomous computers that work together to give the appearance of a single coherent system. So what does that mean? It means that a distributed system is actually middleware. It's actually the glue code, the protocols, the algorithms that allow nodes in a system to work together to appear like a single entity. And the reason I use Cerberus, maybe you're familiar with this similar, this beast. I use Cerberus because first of all, it's a beast, and it also has 3 heads. So it has 3 different brains that need to work together to make this single beast work as a whole, as a single entity. And even more, characteristics of distributed systems are focused or all within this theme of invisibility. So it wants communication between components to be invisible to the user. The system's internal organization should also be hidden from the user. It should be easy to scale. So Cerberus should be able to have 3 heads, 13 heads, 30 heads, 300 heads. It doesn't matter. It should be able to scale to a lot of heads. Components should be independent, so faults should be unknown to the user. Again, everything should be hidden and invisible. And that's why Bear has been able to go along through many years thinking that distributed systems are simple. This is my favorite slide in the entire presentation. It basically sums up life. Nothing is free, nothing is reliable. So the network is unstable. It's not reliable. Bandwidth is not for free. If anybody writing code for distributed systems, who develops distributed systems, makes these assumptions, the distributed system will fail. So these are false assumptions. They cannot be made when you're dealing with something like a system that uses a network and servers. Okay, so first subject in our education of Bear is consensus. Consensus is about communicating and reaching an agreement. Let's look at some code to make this concrete, because it's kind of abstract. Okay, this is consensus at work. When I show examples in this presentation, I'm going to use Elasticsearch or MongoDB, because those are two distributed systems I know. I'll write on the lower right corner what it's coming from, so if you want to follow along with the actual operations in the code, you can refer to that. In this case, we are doing a create index operation using Elasticsearch. And there are two terms to note here. A shard is a subdivision of an index. Shards can be placed in different nodes, and a node is a member of an Elasticsearch cluster. So in the first step, we're creating the index, and we specify wait for active shards 2. Because 2 nodes are available, 2 shards are on 2 separate nodes, the response that we get back is shards acknowledged true. Then we kill a node, and we do the same operation. And what does the response say? It says shards acknowledge false. But it says acknowledge true. So what this is telling you is that I killed a node, but the distributed system kind of talks amongst itself and realizes I killed a node. So it cannot satisfy my request. It cannot satisfy the request that 2 active shards will receive that operation. But it tells me that it hasn't been received by those 2 active shards. So this is an example of consensus. Bear didn't explicitly tell the distributed system that he killed a node. It just learned it on its own through consensus, communication. More formally, consensus is used to achieve overall system reliability in the presence of a number of faulty processes. And then some applications of consensus are choosing a new leader, whether to commit a transaction to a database, and then some real-world examples, PageRank, state estimation, load balancing, and perhaps the most hip example is Bitcoin. Bitcoin uses proof of work to maintain consensus in a peer-to-peer network. Second subject in our education of Bear is synchronization. We have communication, but we also have to be in sync. Maybe you've heard of clock synchronization. Has everybody heard of clock synchronization? Maybe. This is a really difficult problem. Basically, it means how do we get all the nodes in the system to have the same time, be in sync? Because this is so difficult, researchers said, okay, we're trying to get the nodes to have the same time, and time being wall clock time. Wall clock time is the time I see on my watch, on my computer, on my iPhone. That's what we as humans recognize as time. But it's such a difficult problem to solve. Researchers said, okay, let's just back up and ask ourselves, what is time? And I thought at this point in the presentation, everybody might get sick of talking about distributed systems, so we could open up for a discussion on what is art. Just kidding. So what researchers did was say, okay, let's throw out wall clock time. Time is actually really just about the ordering of events in the system, what happens before what. So they use this thing called logical clocks, which is about events happening, and it matters like what happens before what, and that's really just what matters in a distributed system. And that's the way we can have clock synchronization in a multi-node cluster. Okay, we have communication, we have agreement, we're in sync, but we need roles also, so that different nodes don't step on each other's toes. It's important for Bear to know what election algorithm his distributed system uses. MongoDB uses the Raft algorithm. There is also the bully algorithm, the ring algorithm. Knowing more about how the algorithm works or what the algorithm is would help Bear interpret errors coming from his distributed system in the case of an election. Let's look at some code. This is the same code we saw in the beginning when we were looking at how distributed system can be both simple and complex. Here, in between the ping and the insert, anything can happen. An election can happen. And if an election happens, that insert might be sent to a node that can't handle writes. And the message coming back from the distributed system will allow Bear to interpret it and know what he should do next. And knowing what election algorithm his distributed system is using will allow him to know how long he can wait. Or what does it actually mean? Will there be a new primary very soon? Or will this node become a primary very soon? How do the roles get assigned, and how long do they take to be distributed and change? Okay, we have communication, we have synchronization, we have agreement, and we have roles. What about reliability? Let's beef up the distributed system. Okay, so one of the ways we get reliability is by having replication. So having different copies of the same data, or copies of data in the system. But once you have copies of data in the system, then you have this problem of consistency. And we've all heard of data consistency in this problem in distributed systems, I'm sure. Consistency is so difficult. So the only way we can control it is by defining what kind of inconsistency we're willing to tolerate and putting rules and guarantees around that. So we talk about things like axes of consistency. You can have deviations of staleness, of numerical deviation. If you have stock, you can tolerate a certain plus or minus value, numerical value. You can have a deviation in the ordering of update operations. It's good for Bear to understand what kind of consistency guarantees his distributed system has. One of the models of consistency that is relevant to MongoDB in particular, and might be to other distributed systems, is something called causal consistency. Causal consistency is one of the ways that we can kind of control and have guarantees on what consistency we have in the distributed system. What it means, has anybody heard of this? Okay, what it means is that events happening have some kind of vector or relation between them. So there's an inherent ordering that you guarantee. So looking at this example, we have process 1, where we write x equal 1. Then in process 2, we read x equal 1, and we write x equal 3. Process 3 is going to see these as causally consistent operations because it reads the result of process 1 before the results of process 2. Process 4 does not read these events as they're causally consistent because it reads the result of process 2 before process 1. So when you have these guarantees, you allow the client, the user, Bear, his application, know that when he does events or he does operations, they will happen in the order he intends. So MongoDB actually exposes this as an option on a session object. And this was actually one of the last things I worked on before I left MongoDB a year and a half ago. You can create a session object using the client, and you give it the parameter causal consistency true. And then you pass the session object to operations like this find, and further ones, writes, finds, and you know that every time you use that session, every operation you do, you will only ever see the order that you intended in your code. So it's important for Bear to know that he can do this, so he doesn't have any kind of weird race conditions. There's this other consistency model called eventual consistency. Someone's smiling. Do you know what this is? Have you heard of it? It sounds ridiculous because, so first of all, eventual in some languages, like I know German, Italian, French, means maybe. But in English, eventual means it will happen, you just don't know when. There's no guarantee on when. So eventual consistency sounds kind of silly because it's like, okay, eventually your data will be consistent. It's kind of like all bets are off. I don't really want to do the work. Like, you know, maybe it'll be updated someday. But it actually means that you know the data will be consistent at some point, and you're willing to allow for that lag because you don't really care about the data being in sync so much. So I'll give you an example. You update your profile picture on Facebook. Someone you know in Singapore is also looking at your profile on Facebook, one of your friends. They don't see your update right away. Do you really care? Probably not. I hope you don't care so much. But that person, as long as they eventually see that right, it's fine. It might take 5 minutes, but who cares? It's just your profile picture. Anyway, that's eventual consistency. It actually has a lot of applications in the real world because, sorry, a lot of our data is really silly and worthless. Okay, last major subject in the education of Bear is fault tolerance. Using synchronization and consensus, we're able to recover from faults in a distributed system. In order to recover from faults, we have to, again, control and categorize what kind of faults we have. We can have transient faults, which are faults that happen like that, and then they go away, and they don't come back. We have intermittent faults, which are faults that happen repeatedly over a period of time, and then go away. Then we have permanent faults, which are faults that happen and never go away, so an outage that you can't recover from. So in order to recover from faults, we have to have a certain amount of redundancy. We have to have nodes that can step in and take over for other ones when they're not available, nodes with the same copy of the data. You'll find a lot of examples of redundancy in real life. I have 2 lungs, 2 kidneys, hopefully you do too. We have understudies for plays. We always have redundancy when we want to be able to recover from faults in real life. Okay, so Bear realizes by now that distributed systems are complex. Let's look at how smart code can make them simple. Now we're switching over to the beauty part of the talk. See this slide? It's my favorite slide again. This slide now is going to be applied, or we're talking about this slide in the context of Bear's application. So not only if you're writing distributed systems code, which if you are, I'm quite jealous, it sounds really fun. If you make those false assumptions, the distributed system will fail or be a bad distributed system. But also Bear cannot make these assumptions in his application because, as I said, our applications are a myriad of APIs and services, and we have to think about these things and anticipate them and build fault tolerance into our applications. So do not make these assumptions. Okay, so when we talk about these assumptions and faults, we can talk about errors and retrying in the application. Again, we have errors, and we want to categorize them so we can control them and be prepared with code when they happen. So let's categorize them. We have network errors and operation errors. The first kind of network error is a blip, and transient error. So again, something that happens like that, goes away, doesn't come back. But the important thing to know here is that the blip can happen on the way from the application to the distributed system, or on the way back. And we'll see why this matters when we talk about retrying. The second type is an outage. So this is a permanent fault. So a permanent network error, like that. Did someone do that on purpose? It's amazing. I paid someone to do that, actually. I wish I'd snapped my fingers or something. That would have been even better. Okay. Anyway, let's leave it off. I know, I don't know what I'm doing. It's like that was really funny. Okay. Outages. So outages are permanent errors. You can't recover from them. And this is also important when we talk about retrying code for Bear. Now we have operation errors. Operation errors are different from network errors because they're errors that actually come back from the distributed system. And they're really useful because they always tell us what went wrong. So it's important for Bear to identify when he's received an operation error and read the error response and know what it means. So something like not authorized, which can mean that he sent an operation and he's not properly authenticated with the right user roles in order to do that operation. Like something administrative, for example, or like delete, drop the whole database or whatever. He's not authorized to do that. Then there's also an error that could indicate that an election is going on, something like not primary. This is an error for MongoDB. When MongoDB is having an election and the client has sent a write operation to what it thinks is the primary, and there's an election going on and that primary is stepping down and becoming a secondary, and node that can't take the write operation, you will get an operation error back saying not primary. So this is where Bear's knowledge of distributed systems, his knowledge of the election algorithm that his distributed system uses, his database uses, will allow him to interpret this and react appropriately in his code. Okay, so retrying. We understand what the errors are and how they're categorized. So how can we build retry code into the application? This is me, Emily, coming out now and telling you that after 7 years of working on client code for distributed system, I'm telling you and I'm telling Bear that I don't know in my client what operations you're doing and how important they are. So I'm not going to make that call in my code as to whether or not it's safe to retry something. I don't know if you're sending an operation to increase the money in someone's bank account. I don't know if you're increasing a counter. I don't know if you're updating a profile picture. So I'm not going to make that call. But as a client engineer or maintainer, developer, I make options available to Bear so that he can use them to write the correct retry code into his application. So you can't rely on the client to make this call for you. You have to decide yourself when it's safe to retry and how to retry. Let's look at an example. This is using MongoDB. It's an update operation that the first document hash is a match query. So it'll match a document with that ID, and then it'll increment a counter by 1. And if it doesn't find the document, it'll create the document. So it's an upsert. What could possibly go wrong? Let's look at our different type of errors and see what kind of retry code we would want to write in theory in order to make sure that this update goes through. In the case of a network blip, we probably want to retry once, because as I said, a blip is something that happens and then goes away. So if we retry once, it'll go through. But again, remember that if I get a network error, I don't know if it'll look the same to the application, right? So I don't know if the update got to the server and then had an error on the way back or a network error on the way back, and the counter or the bank account was actually incremented in some way. So that's important to know when you write retry code. So you might want to retry once in that case. For an outage, it depends. You might want to retry, but with a limit. If you think in the case of an outage, when you get repeated network errors, maybe you want to retry. There are a lot of different ways to do it. You could do a back-off strategy where you retry, but you increment the interval that you wait in between each retry. You could retry for a certain period of time. You could retry n times. A lot of different things you can do, and it's up to Bear to make that call, how long he's willing to make the user, if there's an end user using a browser trying to do this operation, how long he's willing to make that user wait in order to get the operation to go through. In the case of not authorized, you probably don't want to retry, because if you're not authorized to do an operation, you're probably not going to be authorized to do it if you try again. And if you are, there's probably something wrong. Not primary, as I said, indicates that there's an election going on in the case of MongoDB. So you might want to wait, depending on how long you think the election would take to happen, how big your cluster is. I don't know, you should do some testing and figure out how long elections take, what version of the distributed system you're using is, because I know election algorithms are always being improved. So again, there's not one right answer to this. But the key to doing all this, the key to retrying, all of this, like when you retry, how long, all that stuff, is kind of up to the application developer. But everybody, Bear included, should make sure that when he's retrying operations, especially writes, that they should be idempotent. Who knows what idempotent means? Who wants to tell me what it means? Nobody ever wants to tell me. So I'll tell you. Idempotent operations are operations that no matter how many times you do them, they will only ever be applied once. So I write an operation such that if it goes through once and I do it again, the effect will not be done twice. Does that make sense? Okay. Let's look at an example in MongoDB and Elasticsearch and see how we can write idempotent operations so that it's safe to retry them. MongoDB is a little bit obscure with this. It's not as straightforward as Elastic, but we'll look at it anyway. So in MongoDB, you create a unique value. We set it to a variable unique. Then we do this update operation. We match it on the ID, and then we push, or we add to set this unique value, the document pending unique value. And the set is a data structure in a MongoDB document. That's a set, so it has unique values. And it's upsert true. So if I need to retry this, it'll only ever create the document once. Then, when I do the update and I increment a counter here, this is my operation, the write, I will match on the ID and the unique value. And what's important to understand about MongoDB here, and this is where it's important for Bear to know how MongoDB works, is that this is an atomic operation. So nothing can happen between the matching of the document and the update operation. The update operation removes the unique value from the set and increments the counter. So nothing's going to happen in between these two, so that means it matches updates all in one step. So that means that if he retries this operation, it won't increment that counter a second time because that match will fail the query. Make sense? So that's how you can do idempotent operations with MongoDB. It's just an example, but it's important to look into this if you want to retry operations and make sure that they're idempotent, especially when you're doing things like incrementing counters and things like that. So as I said, Elasticsearch makes this a little bit more straightforward. So it's called optimistic locking. So if you want to look it up, you can look up this term, optimistic locking. It's essentially the same thing. But the key here is that Elasticsearch has versions with its documents. So you can query for the document you want to update, get its version, and then this next slide. You can include the version in the match criteria when you want to do the update. So when you do the update, you say version 1 because that's what we saw on the previous slide. It reported the version was 1. And then if I retry this and it has already happened, it's idempotent because Elasticsearch will respond and say, the current version 2 does not match the one that I asked for, 1. So it won't increment the counter unless the version matches. So you should use this to your advantage. You should use these versions if you want to be able to retry safely. Okay, that's idempotent operations. Really important for Bear to understand if he wants to write retry code into his application. Gem APIs. Now I put this in here because after 7 years of responding to issues and helping people understand a distributed system and write better code, write more robust code with it, I think it's important for people to understand the gems that they're using, especially ones that are clients to these complex systems, because they do their best to expose behavior and options and error messages to you so that you understand how to use them well. So it's good for Bear to research what does his client do in the case of a network blip? What kind of error will he expect? What about when a primary is unavailable? Network outage, operation failure. If he learns about all of this, he'll be able to use the client more effectively. Also, the client exposes options, as I said. This is a mashup of the MongoDB driver and the Elastic options. And I guess to illustrate to you how you can use these to your advantage is something like heartbeat frequency in MongoDB indicates how often, so the driver has a background thread that pings the cluster, the MongoDB cluster, and checks whether nodes are up or down and what their roles are, and keeps track of the state of the cluster. The heartbeat frequency by default is 10 seconds, but if you want your code to be able to detect an election faster, you could decrease the heartbeat frequency to something like 5 or 3. But again, keep in mind that that's going to be requests on the network because you're pinging all of these nodes. So it's a trade-off. You really need to think about what you're doing and how you're using these options. But the options are there. The client maintainers make them available to you and to Bear so that they can write their code better. So it's worth checking them out. Okay, last subject is testing. Now this next slide is as much for me as it is for Bear. But testing against single server running on localhost is not sufficient. I love testing my gems, my clients, on single server running on localhost because they always pass. I mean, if my tests pass, they'll always pass. But as soon as I introduce a network, as soon as I introduce a real distributed system, like real in the sense that there are multiple nodes, then my code's actually being tested and it might not work. So there's no reason why you should test your application on a single server running on localhost if your application's running in production with a whole cluster of nodes using networks. So this is my favorite slide. I don't know if you recognize it. It's disguised as a testing slide. But we can turn all of these false assumptions into tests. So you want to make sure that you're using a network, not localhost. You want to use a shared instance, use threads, stress test. Run your test and then kill a node in the middle of it and see what happens. Does your test just totally crash and shut down? Do you end up having retry code in there that ends up duplicating data or incrementing bank accounts when they shouldn't, or more than once? So these are all things that Bear needs to think about and you need to think about when you're writing tests. Those false assumptions also apply. Okay, so Bear's feeling a little overwhelmed, but he's really grateful for all this new knowledge and is eager to look into his distributed system and learn more about the options his client has available and how to write better retry code. But he actually texted me this morning, and I want to share with you our conversation. He said, I have a quick question. Apparently he's working today. I don't know why. Apparently the team is having an issue with race conditions when persisting to Redis. Would you consider wrapping the Redis persistence code in a mutex? Just wondering if that would make sense. And so see, these are some of the things I asked. I said, well, I thought you understood what we were talking about, but apparently not so much. I said, what is your Redis topology like? How many nodes are you connecting to? Does Redis, what kind of guarantees does Redis have? Like, is it just kind of the Wild West? You just like put in operations and they can be applied in whatever order they want? Or does Redis guarantee some ordering of operations? What does the client you're using guarantee? Do you have to opt in to a guarantee on update, update of order operations? Who's initiating the requests? Where are they coming from? Are they background jobs? Are they clients using your website? Are they mobile apps? Like, are you expecting that all of these things are happening in some kind of specific order when they're actually all different like systems with different requests? Again, this is where knowing how distributed systems works is applicable to Bear's application, because he has all these different services, and if he expects all of them to be in sync, it's kind of a false assumption. Has there been any failovers or change of state in the Redis servers? Did they upgrade? Is there now like a new election algorithm or like different roles or something? I don't know. There are a lot of questions that I asked him, and we had a long conversation. And I'm happy to report that now he's happy and he's writing better code. And that's it. Thank you.